We thought we understood physics. Until the sun got hotter the farther you move away from it. Until gravity crushed atoms into a slop. Until a particle smaller than an atom carried the energy of a thrown baseball across the universe. Turns out we understood less than we thought. Bizarre space phenomena that defy physics. Neutron stars. Neutron stars start out as absolutely huge stars. The kind that burns way too bright and way too fast, chewing through nuclear fuel. When that fuel runs out, there's no longer outward pressure from fusion to hold the star up against its own gravity. The core collapses. The outer layers rebound off that collapse and explode outward as a supernova, one of the most violent events the universe has to offer. What's left behind is the core, and this core doesn't become a planet or a white dwarf or anything familiar. If the mass is just right, not enough to become a black hole, but way too much to stay normal, it collapses into a neutron star. The sun is about 1.4 million kilometers wide. A neutron star takes more mass than that entire sun and squeezes it into a ball only about 20 kilometers across, roughly the size of a city. If you took a teaspoon of neutron star material, it would weigh more than Everest. At this point, matter is no longer behaving like matter as we know it. In normal life, atoms exist because electrons orbit nuclei, and electromagnetic forces keep everything nicely spaced. Chemistry is built on that spacing. Bonds, molecules, materials, everything relies on electrons having room to exist. Inside a neutron star, gravity says no. As the core collapses, electrons get squeezed harder and harder. Eventually, quantum mechanics steps in. Electrons don't like being compressed into the same state, thanks to the Pauli exclusion principle, which basically says you can't stack identical particles on top of each other. That resistance creates electron degeneracy pressure, which can hold up smaller collapsed objects like white dwarfs. But neutron stars don't stop there. The gravity is so extreme that even electron degeneracy pressure fails. Electrons get forced into protons, combining through a process called electron capture, producing neutrons and neutrinos. The neutrinos escape. The neutrons stay. This is the conundrum. No electrons means no atoms. No atoms means no elements. No elements means no chemistry. Matter is no longer organized into nuclei surrounded by electrons. Instead, it becomes a degenerate neutron fluid, a state of matter that does not exist anywhere else in the universe in stable form. Neutron stars aren't uniform. They're layered, and each layer represents matter being crushed past another familiar boundary. The outermost region is a thin crust where nuclei still exist, but they're jammed into a lattice surrounded by a sea of free electrons. As you go deeper, nuclei become more neutron-rich, leaking neutrons like they're under pressure because they are. Then things get weird. At certain depths, nuclear matter rearranges itself into shapes physicists casually refer to as nuclear pasta. These aren't molecules. These are structures formed by a tug-of-war between nuclear forces and electromagnetism. Matter organizes into shapes nicknamed lasagna, spaghetti, and gnocchi. Not because it's cute, but because that's genuinely the best way to describe what happens when nuclei are crushed until geometry itself starts improvising. For us to get a Michelin star, make the best pasta dish the world has ever seen, everything depends on this. Yes, I guess. Why do we have 3 different pastas? They were under a lot of pressure. I should have just asked for one pasta dish. You think? Below that, individual nuclei stop existing altogether. You enter the neutron superfluid, where neutrons flow collectively in a quantum state with zero viscosity. This isn't liquid in the everyday sense. It's a macroscopic quantum object behaving more like one giant wave than a collection of particles. So, neutron stars take matter, crush it past atoms and chemistry, and leave behind something that barely follows the rules physics was built on: corona of the sun. At the visible surface of the sun, the photosphere, the layer that actually shines, temperature is at about 5,800 Kelvin. That's already hotter than anything we deal with on Earth. Do I smell bacon? I opened Chrome. Yeah, that checks out. This is the layer where energy that started in the sun's core finally escapes as light. As you move away from that surface, through the sun's atmosphere, the temperature doesn't drop. It explodes. The outermost atmosphere, the corona, reaches over 1,000,000 Kelvin, sometimes several million, and during solar eruptions, parts of it spike far higher. This means gas that is extremely thin, barely there at all, is somehow much hotter than the dense glowing surface beneath it. Temperature isn't about how bright something looks, it's about how fast particles are moving. In the corona, electrons and ions are zipping around with enormous energy. So the question scientists have been wrestling with for decades is simple to say and hard to answer: where is that energy coming from? It can't just be heat leaking upward from the sun's surface. If that were the case, the corona would cool off quickly. It also constantly loses energy by radiating light and by feeding the solar wind, a stream of particles that escapes the sun and fills the entire solar system. something has to be actively pumping energy into the corona all the time. The sun is not just a hot ball of gas, it is a plasma, meaning its particles are electrically charged, and charged particles obey magnetic fields. The sun's interior is in constant motion. Hot plasma rises, cool plasma sinks over and over again. This churning motion drags magnetic field lines with it. Because plasma conducts electricity, the magnetic field gets twisted, stretched, braided, and stressed. Magnetic fields aren't passive, they store energy, and when you stress them enough, they find ways to release that energy into the surrounding plasma. This is where the corona gets heated, not by warmth drifting upward, but by magnetic energy being converted into particle motion. One way this happens involves Alfvén waves. These are not sound waves. They're waves that travel along magnetic field lines themselves. When the sun's surface moves, it sends these waves upward into the corona, carrying energy with them. If those waves break down into turbulence or get damped, their energy transfers directly into particles, making them move faster, raising the temperature. Another major process is magnetic reconnection. Magnetic field lines don't like being tangled forever. When they snap and rearrange into a lower energy configuration, the excess energy gets dumped into the plasma around them. This release can be sudden and violent, like a solar flare, or incredibly small and frequent. Scientists think the corona may be heated by countless tiny reconnection events, often called nanoflares, each too small to notice on its own, but together adding up to a massive energy input. What makes this even stranger is that the temperature jump happens across a very thin layer called the transition region. Over a short vertical distance, the temperature skyrockets from tens of thousands of Kelvin to over 1,000,000. That tells us the heating isn't spread evenly. It's tied to magnetic structure and plasma behavior, not distance from the core. Ultra-high energy cosmic rays. Space sometimes fires particles at Earth with so much energy that according to our physics, they shouldn't exist. These are called ultra-high energy cosmic rays. And despite the name, they're not rays. They're individual particles, usually protons, sometimes heavier atomic nuclei, moving so fast and carrying so much energy that they break every comfortable idea we have about how particles behave. Cosmic rays in general are normal. They hit Earth constantly. Most come from the sun, supernova remnants, or other energetic but understandable sources. They're fast, sure, but still reasonable. Ultra-high energy cosmic rays are not reasonable. The most extreme ones carry energies above 10 to the power 20 electron volts. That's one single proton hitting Earth with roughly the kinetic energy of a fast-thrown baseball. Nothing humanity has ever built comes close. Even the Large Hadron Collider, our most powerful accelerator, is weaker by orders of magnitude. These particles are already moving as fast as physics allows, so extra energy doesn't make them faster. It makes them almost impossible to deflect. Cosmic magnetic fields that easily bend ordinary particles barely touch them, which is why tracing them back to their source is so hard. Physics also says they shouldn't survive long journeys. The universe is filled with background radiation, especially the cosmic microwave background, which should drain energy from ultra-energetic particles over distance. There is predicted maximum energy they should be able to keep over long distances called GZK limit, and yet some particles clearly exceed it and still reach Earth. That leaves a problem. Either they're being created relatively nearby in extreme environments like black holes, relativistic jets, or gamma ray bursts, or something about how they gain or keep energy isn't fully understood. When these particles hit Earth, they create enormous atmospheric particle showers. From those, scientists reconstruct energy so high they push the limits of known physics, making ultra-high energy cosmic rays one of the clearest signs that the universe can still surprise us. And that's all for today. Thanks for watching.